Hi everybody. Today we learn Lagrange's mean value theorem. So in the previous lecture we study about Rowley's theorem, and if we compare Lagrange's mean value theorem, which we also call as LMVT. L means Lagrange's, M means V means value, and T means theorem. Lagrange's mean value theorem, shortcutly denoted by LMVT. Then if we have to verify or if we have to check the conditions of Lagrange's mean value theorem, so first we examine some conditions of the functions. So if the given function be a polynomial function and satisfy the first condition, which is f is continuous on closed interval AB, and second condition, f is also differentiable on open interval A comma B, then there exists such a condition at any point C, which is C, then there exists at least one point C such that f dash of C is equals to, by using this condition, f dash of C is equals to f of B minus f of A upon B minus A. We can find the value of C, and C belongs to A comma B. If we satisfied these all the conditions of LMVT, f is continuous on closed interval AB, f is differentiable on AB, and point C which exists in this function at x is equals to C, then by using f dash of C is equals to fb minus f upon b minus a, we can find the value of C. So, and if the value of C is in between A and B, then we can say that we verified Lagrange's mean value theorem. So the statement of Lagrange's mean value theorem, we can write Lagrange's mean value theorem state that Lagrange's mean value theorem state that for any real value, a differentiable function which is continuous at two endpoints, there is at least one endpoint at which the tangent is parallel to the second through its endpoint. This statement we can verify by using geometrical significance. So its a geometrical significance is, so if we draw any curve on a coordinate axis, first geometrical significance, which is first we draw, if we draw the curve which is y is equals to f of x on a coordinate axis, so we take this y axis, x axis, and we take any curves on a coordinate axis which is like this. So if we draw the curve which y is equals to f of x on a coordinate axis, and its coordinate axis point A, here we take the point A, and this coordinate A comma f of A, x coordinate A, y coordinate f of A, at a point A comma f of A, and if we take here point B comma f of B, here the x coordinate is B and the y coordinate is f of B, on the curve on the curve, then slope of the chord, then the slope of the chord AB, slope of the chord AB is equals to f of b minus f of a upon b minus a. Then the slope of the chord f of b, f AB is f of b minus f b minus f a upon b minus a. The line which is point to line which is passing through point C, which is a tangent. So here distance A, B, C, we can say f of A, f of B, f of C. So here, and we know that since by the statement of Lagrange's mean value theorem, we can write f dash of C is equals to again f of B minus f of A upon B minus A at point A comma B. So from the above equation 1 and equation 2, we can say that from 1 and 2, we can say that f dash of C means slope of chord AP, slope of chord AB. Hence equation 1 and 2, we can say that f dash of C is equals to slope of chord AB. This show that the tangent to the curve y is equals to f of x. This show that tangent to the curve y is equals to f of x at a point x is equals to c is parallel to the chord AB, which is both are parallel to chord AB. So the first example of Lagrange's mean value theorem. The example number first, verify Lagrange's mean value theorem for the function f of x is equals to under root of x plus 4 on the interval 0, 5. It is clear that here we have to verify that the given function, which is y f of x is equals to under root of x plus 4, which satisfied the conditions of LMVT at 0, 5 or not. So if I have to verify the conditions of Lagrange's mean value theorem, then first we take given function f of x is equals to under root of x plus 4, which we give equation number 1, is a polynomial function and it is continuous on closed interval 0, 5 and differentiable on also open interval 0, 5. But by Lagrange's mean value theorem, we can say that so the LMVT is applicable for the function. So LMVT is applicable for a function at any point C is f dash of C is equals to f of b minus f of a upon b minus a, and C belongs to a comma b. Here the value of a comma b represented by 0, 5, hence a is equals to 0 and b is equals to 5. Here we have to verify that whole this condition, we have to calculate the value of f dash of C, again f of b, again f of a, and the value of b which is 5 and the value of a which is 0. So first we take the given function f of x. If we differentiate with respect to x, if we differentiate equation 1 with respect to x, then we get the value of f dash of x is equals to derivative of under root of x plus 4, which is 1 upon 2 under root of x plus 4, and again derivative of x plus 4 is 1. So f dash of x is equals to 1 upon 2 under root of x plus c. From this above we can find the value of f dash of c. When at x is equals to c, we can write f dash of c is equals to 1 upon 2 under root of c plus 4. So here, which is the value of f dash of c. Now again we have to find f of a. By using the value of f of x, we can find the value of f of a, and under root of 0 plus 4 under root 4, which is a 2. So again value of f of b, when b is equals to 5 under root of 5 plus 4, which is under root 9. The value of under root 9 is 3, which is equation number. We can write this here, equation number 3 and equation number 4. So from equation a, 2, 3 and 4, we can write the value of f dash of c, which is 1 upon 2 under root of c plus 4. Value of f of a and f of b is 3 minus f of a is 2 upon b minus a means 5 minus 0. So we can write this 1 upon 2 under root of c plus 4 is equals to 3 minus 2, which is 1 by 5. Again we can write this 2 under root of or c plus 4 is equals to 5 upon 2. Under root of c plus 4 is equals to 5. If we take square both sides, squaring both sides, square and square root get cancelled. C plus 4 is equals to square of 5, which is 25, and square of 2 is 4. If we shift this 4 right side, we get 25 by 4 minus 4. If we equate denominator of this both term, we can write 25 minus 4 into 4, 16 upon 4. 25 minus 16, which is 9 by 4. And this 9 by 4 is belongs to the value of a, means in between 0 and 5. Hence we can say that Lagrange's mean value theorem are verified. So again next example number 2. Here again we have to verify that Lagrange's mean value theorem. For the functions f of x is given x plus 1 by x and is all lie on the interval in between 1 and 3. It means that at any point c which belongs to open interval 1, 3. So here we have to find LMVT, means Lagrange's mean value theorem. If we have to verify Lagrange's mean value theorem, then we know about the conditions of LMVT or Lagrange's mean value theorem. So first we take given the function f of x is equals to x plus 1 by x, be a polynomial function, be a polynomial, which we give equation number 1, be a polynomial function, and it is continuous on closed interval 1, 3, means value of a is 1 and value of b is 3. Again, it is differentiable on open interval 1, 3. So such that if LMVT, Lagrange's mean value theorem, is applicable for at any point C, then f dash of c is equals, then it satisfies f dash of c is equals to f of b minus f of a upon b minus a at c belongs to a comma b. So which is equation number 2. If we have to verify the LMVT, Lagrange's mean value theorem, then we have to prove that this c is related to a comma b by using f dash of c, which is fb minus fa upon b minus a. If we have to find the value of c, then first we evaluate f dash of c. After that, f of b means 3, f of a means 1. So here we can write the value of a comma b or a comma f of a represented by 1 comma 3. Here we can write a is equals to 1 and b is equals to 3. From above we can write the value of f of a is equals to f of 1 is equals to 1 plus 1 by 1 is 1, 1 plus 1 which is 2. So again we have to find the value of f of b means f of b means 3 and b. So if we put the value of x at 3, we can write 3 plus 1 by 3. The cross product of this 3 plus 1 by 3 is 3 to 3, 9 plus 1 upon 3, which is 10 by 3, equation number 4. So now we can say that we can find value of f of b, f of a similar to f dash of c. So we take equation 1 become, and the equation 1 which is f of x is equals to x plus 1 by x. After differentiating we get the derivative of x, and the derivative of f of x which is f dash of x, derivative of f of x which is 1, and the derivative of 1 by x is 1 by x square. At the point x is equals to c, we can find the derivative f dash of c 1 minus 1 upon c square, which is equation number 5. So from 2, 3, 4 and 5, from 2, 3, 4 and 5, if we substitute the value of 3, 4 and 5 in equation 2, the value of f dash of c which is 1 minus 1 upon c square, value of f of b is 10 by 3 minus the value of f of a which is 2 upon b minus a means value of b which is 3 minus 1 is equals to, if we take cross product of both, we can write 10 minus 6 upon 3 into 1 upon 3 minus 1 which is 2. 10 minus 6, 4 upon 3 into 1 by 2. 2 is 1, 4 is 2. 1 minus 1 upon c square is equals to 2 by 3. If we shift 1 by c square right side, we can write 1 minus 2 by 3. 3 into 1 which is 1 upon c square is equals to 3 minus 2, 1 by 3. That is, we can write c square is equals to 3 and the value of c which is plus or minus under root 3. Here the value of c which is 2 is plus under root 3 and minus under root 3. In between 1 and 3, every positive number which is under root 3 is belongs to 1 comma 3, but minus root 3 does not belong to 1 comma 3. Hence we can write under root 3 belongs to 1 comma 3 which is c, but minus under root 3 does not belongs to 1 comma 3. So if any numbers which is under root 3 belongs to 1 comma 3, we can say that we verify Lagrange's mean value theorem at c is equals to under root 3 which is belongs to 1 comma 3. Hence we verified Lagrange's mean value theorem. By the similar way, we can take first last question of the exercise number 2.3, which is depend on Lagrange's mean value theorem. First we take this question number 7, verify Lagrange's mean value theorem for the following function, because we have to continue Lagrange's mean value theorem, the part of Lagrange's mean value theorem. So in this question there are 6 sub questions. First we have to solve the first question. F of x is equals to log x on 1 comma e, and here we have to verify that Lagrange's mean value theorem. By using Lagrange's mean value theorem or LMT, we have to verify f of x is equals to log x on 1 comma e. So first we know about how to check the given function is applicable for LMT, means Lagrange's mean value theorem or not. So first we take given a function, and the function f of x is equals to log of x is logarithmic function. Given function is in the form of logarithmic function. Hence, if the function is logarithmic form, it is continuous for all real valued function. Hence we can say that it is continuous. Therefore it is continuous at 1 comma e and differentiable at open interval 1 comma e. So we know that function applicable for Lagrange's mean value theorem at x is equals to c, f dash of c is equals to f of b minus f of a upon b minus a. Here open interval 1 comma e means coordinate represents 1 comma e. We can say that here the value of a is 1 and the value of b is e. So by using this value and function, we can find f dash of x, f of b and f of a. So we give it equation number first. After that, if we have to find the value of a, f of a is equals to, the value of a is 1, is equals to log 1, and we know that the value of log a or log 1 which is 0. Again f of b is equals to f of value of b is e, which is log e, and we know that the value of log e is 1. So from the function f of x is equals to log x, we have to find first log f dash of x, and if we replace the value of x which is c, then we get f dash of c. If we differentiate with respect to x, we get derivative of fx which is f dash of x and derivative of log x which is 1 by x. So at x is equals to c, we can write f dash of c is equals to 1 by c. We give it equation number 2, equation number 3 and equation number 4. Put 2, 3, 4 in 1, we get f dash of c which is 1 by c is equals to f of b means 1, f of a minus 0 upon b minus a means e minus 1. Hence we can write it. If we take a cross product of 1 upon e minus 1, we can write e minus 1 is equals to c, or we can write c is equals to e minus 1. Hence the value of c which is e minus 1. Upper limit of the given function is e, and hence we can say that e minus 1 related to open interval 1 comma e. Hence we can write LMVT means Lagrange's mean value theorem is verified. We can write it Lagrange's mean value theorem is verified. So the next one, question number 2. Example number 2 in question number 7 is f of x is equals to x minus 1, x minus 2, x minus 3 on closed interval 0, 4. Again here we have to verify that Lagrange's mean value theorem. So if we are to verify LMVT, then we can write given a function, and the function is f of x is equals to x minus 1, x minus 2, x minus 3 be a polynomial function. If it is polynomial function, then we can write it is continuous at closed interval 0, 4 and differentiable at or on open interval 0, 4 at any point C. Therefore, Lagrange's mean value theorem is applicable for, we can write it f dash of C at x is equals to C at any point C. F dash of C is equals to f of B minus f of A upon B minus C. So we can write this f dash of C is equals to f of B minus f of A upon B minus C. So also we can write value of f of 4 minus f of 0 upon B minus C. Hence we can write here the value of A is 0 and the value of B is 4. By using this value A, B and f of x, we can find f dash of C, f dash of A, f dash of B. First we find that f of A, first we find that f of A is equals to, when A is 0, f of 0 and the value of f of 0 is 0 minus 1, 0 minus 2, 0 minus 3. So we can write it 0 minus 1, which is minus 1, minus 2, minus 3. Minus 1 into minus 2 plus 2 plus 2 into minus 3, which is minus 6. Again we can write the value of f of B, which is f of, we can write 4 is equals to 4 minus 1, 4 minus 2, 4 minus 3. 4 minus 1, 3, 4 minus 2, 2, 4 minus 3, 1. We can write 3 into 2 into 1, which is 6. So, by using the function f of x, and f of x is equals to x minus 1, x minus 2, x minus 3, we can find f dash of x, and at x is equals to c, we convert this f dash of c. So, if we multiply whole three brackets, we can write x into x into x, which is x cube, plus, so x into minus 2 minus 2x, minus 2x into minus 3, we can write, or first we solve first two brackets, x into x, x square, minus 2x minus x minus minus plus 2 into x minus 3. Again we can write it x square minus 3x plus 2 into x minus 3. If you multiply again these two brackets, we can write x square into x, which is x cube, minus 3x square minus 6, sorry, x cube minus 3x square plus 2x, again minus 3 into x, minus 3x square minus minus plus 9x minus 6. Hence we can write it x cube minus 3x square minus 3x square minus 6x square plus 2x plus 9x plus 11x minus 6, which is the value of fx. So after differentiating with respect to x, we can evaluate f dash of x. So differentiate with respect to x. The value of f dash of x is equals to derivative of x cube 3x square minus 6 into derivative of x square, which is 2x, 6 into 2, which is 12x, plus derivative of 11x, which is 11, minus derivative of 6, which is 0. So at x is equals to c, we can write f dash of c is equals to 3c square minus 12c plus 11. Therefore, we can write this whole value in equation 1. So equation 1 becomes the value of f dash of c, that is 3c square minus 12c plus 11 is equals to f of b minus f of a means 6 minus minus plus 6 minus 6 upon b minus a means 4 minus 0. We can write this 3c square minus 12c plus 11, 6 plus 6, which is 12 by 4. We can write it 3c square minus 12c plus 11 is equals to c. If we take this 3 left side, we can write 3c square minus 12c plus 11 minus 3 is equals to 0, means 3c square minus 12c plus 8 is equals to 0. Now we have to factorize this 3c square minus 12c plus 8 is equals to 0 to finding the value of c. But here we can take the factor of 8 into 3, which is 24, for remaining minus 12. So we can find the value of c by using the formula c is equals to minus b plus minus under root of b square minus 4ac upon twice a. So here a means coefficients of c square, b means coefficients of c, and c means constant function. If we substitute this value abc, if we compare ac square plus bc plus c is equals to 0, we can write c is equals to minus b, means value of b is minus 12, minus of minus 12 plus minus under root of b square means minus 12 square minus 4, value of a which is 3 and the value of constant function which is 8 upon 2 into a means 3. Again minus minus plus 12 plus minus under root of square of minus 12 144 minus 8 into 3 24, 24 into 4, we can write the value of 24 into, which is 4 into 8 32, 32 into 3 96 upon 2 into 3. So we can write again 12 plus minus under root of 144 minus 96 is 48 upon 2 into 3. This 48 is a term which is square multiple. If 4 is a square of 2, and if we multiply this term, we can write 12 plus minus under root of 4 into 12 upon 2 into 3. So if we take this 4, taking us out of square root, we can take 2 common from this both term. Here we can write 6 plus minus under root of 12 upon 2 root 3. So here 2 get cancelled. We can take again here, or we can write 16 into 3. 16 into 3. So we can take 16 square root of 16. 4 common from this both term, we can write 2 is 1, 4 2, 2 into, here we can write 3 plus minus under root 3 upon 3. So, or we can write 3 into 2 again, which is 6, 4. We can write this 6 plus or minus 2 under root 3 upon 3. If we take separate term, we can write 6 upon 3 plus minus 2 root 3 upon 3. So here 3 is 1, 6, 2. 2 plus minus root 3 get cancelled. 2 upon root 3, which is the value of C. And here we can say that C is belongs to 0, 4 because 2 plus or 2 minus both term in small increment which is belongs to 0, 4. Hence LMVT is verified. We can say that Lagrange's mean value theorem is verified. So the next example number 3, f of x is equals to x square minus 3x minus 1, and x belongs to first coordinate the value of a which is minus 11 by 7 and the value of b which is 13 by 7. So now we take given function, and the function which is f of x is equals to x square minus 3x minus 1 is polynomial function. Polynomial function. And it is continuous, and it is continuous on a closed interval minus 11 by 7, 13 by 7, and differentiable on open interval minus 11 by 7 and 13 by 7. So LMVT is applicable at any point x is equals to c, which is f dash of c is equals to f of b minus f of a upon b minus a, which is equation number 2. So here we can say that the value of a which is minus 11 by 7 and the value of b which is 13 by 7. From this value of a and b we can find f of a is equals to f of minus 11 by 7 is equals to f dash f of a which is minus 11 by 7 whole bracket square, again minus 3 into x means minus 3 into x is minus 11 by 7 minus 1. So square of minus 11 121 upon square of 7 49 minus minus plus 11 into 3 33 upon 7 minus 1. If we can take a equal denominator, then the term 121 plus 121 as it is, plus if we multiply it denominator by 7, we can write this 33 into 7 which is 231 and 49 into 49 which is minus 49. The sum of 121 plus 231 minus 49, we can write it minus 153 upon 49, minus 153 upon 49. Sorry, not a minus, 303 upon 49. 303 upon 49. Now we have to calculate again the value of b. So we have to find f of b is equals to f of b means we have to find again value of b which 13 by 7. We can write 13 by 7 bracket square minus 3 into 13 by 7 minus 1. The square of 13 which is 169 upon 49 minus 13 into 3 39 upon 7 minus 1. If we take an equal denominator of both three terms, we can write 169 as it is. If denominator is 7 and we have to denominator which is 49, then we can write 49 into 7, 273 minus 49. The sum of 169 minus 273 minus 49, which is minus 153 upon 49 denominator as it is, which is the value of f of b. So now we have to take first the function which is f dash of c. So function become, now equation 1 become, and equation 1 which is f of x is equals to x square minus 3x minus 1. After differentiating with respect to x, we can write a derivative of fx which is f dash of x, derivative of x square which is 2x minus 3 into derivative of x1, and the derivative of minus 1 is 0. So we can write at x is equals to c, f dash of c is equals to 2c minus 3. If we put this whole value which is f of a, value of f of b, and value of f dash of c in equation 2, first we write the value of f dash of c 2c minus 3 equals to f of b means minus 153 upon 49 minus f of a means 303 upon 49 upon b minus a, the value of b which is 13 by 7 minus a means minus 11 by 7. So we can write denominator equal minus 153 minus 303 upon 49 upon, if denominator of 7 equal, we can write 13 minus minus plus 13 plus 11. So here we have to find the value of c, minus 153 minus 303, which is minus 456 upon 49 as it is, divided by 13 plus 11, which is 24 upon 7. We can write this term in multiple form, minus 456 upon 49. After interchanging numerator denominator, we can write multiple of 7 upon 24. 7 1 24 as 7. We can divide again by 8 into 3, 8 into 57, which is minus 57 upon 7 into 3, which is 21, which is the value of 2c minus 3. If we shift this minus 3 right side, we can write 2c is equals to minus 57 upon 21, minus become get plus 3. If we take equal denominator, then we multiplied 3 by 21, which is 3 into 2 63 upon 21. Minus 57 plus 63, we become 6 upon 21, the value of 2c. If we shift this c right side, here we can write 3 into 2 6, 3 into 7 21, 2c is equals to 2 by 7. If we shift this c right side, we can write c is equals to 2 by 7 into 1 by 2. Here 2 get cancelled, the value of c which is 1 by 7. And we can say that c belongs to a comma b because 1 upon 7 is really belongs to minus 11 by 7 to 13 by 7. Hence LMVT is verified. So the next example number 4, and here f of x is equals to 2x minus x square, x belongs to 0, 1. Also we have to verify that Lagrange's mean value theorem or LMVT. So first we take a given function f of x is equals to 2x minus x square, which we give equation number 1, be a polynomial function, and hence we can say that it is continuous at closed interval 0, 1 and differentiable at open interval 0, 1. So we can write Lagrange's mean value theorem is applicable at x is equals to c is f dash of c is equals to f of b minus f of a upon b minus a. By using this solution, we can find the value of c. And if value of c is related to in between 0 and 1, then we can say that LMVT is proved. So here we can say the value of b, which is a, value of a which is 0, and value of b which is 1. By using this value of a and b, we can find f of a means f of 0. If we substitute the value of a, x in g is 0 in equation number 1, we can write 2 into 0 minus 0 square, which is 0 minus 0 is equals to 0. Again the value of f of b means f of 1, which is 2 into 1 minus 1 square. The value of 2 into 1, 2 minus 1 square, which is 1. 2 minus 1 is 1. Again we have to find f dash of x at f of x is equals to 2x minus x square. After differentiating with respect to x, derivative of f is f dash of x, derivative of 2x which is 2 minus the derivative of x square which is 2x. At x is equals to c, we can write f dash of c is equals to 2 minus 2c. So this value of f dash of c, value of f of a and value of f of b put in equation 2. So equation 2 become, we can find the value of c. F dash of c, left hand side, which is f dash of c, 2 minus 2c. The value of f of b, which is 1, value of f of a minus 0. Here we can write again value of b 1, value of a 0, 1 minus 0. Here 2 minus 2c is equals to 1 upon 1, which is 1. If we take this 2c right side, we can write 2c is equals to 2 minus 1. 2c is equals to minus 1, 1. C is equals to 1 by 2. So this value of c, which is belongs to a comma b, because 1 by 2 belongs to in the open interval 0, 1. Hence we can say that Lagrange's mean value theorem is verified. So the next example, f of x is equals to x minus 1 upon x minus 3 on closed interval 0, 4. We know that the function, given function, and this function f of x is equals to x minus 1 upon x minus 3 is a rational function. Rational function. But here it is clear that if we put the value of x is 3, then 3 minus 3 is 0, and if the value of denominator is 0, then their value of function is infinity, and infinity does not exist in the functions. So we can say that the function which is f of x is continuous at closed interval 0, 4 and differentiable at open interval 0, 4 except 3. Except 3. Here we can't accept the value 3. We can accept the value of c, which is 3, because 3 does not exist in the function. So we know that LMET is applicable for x is equals to c, f dash of c is equals to f of b minus f of a upon b minus a. Here we know that the value of a, which is 0, and value of b, which is 4. If we substitute this value of a and b, then we can say f of a is equals to f of 0, and the value of f of 0, which is, if we substitute the value of x0, 0 minus 1 upon 0 minus 3 minus 1 by minus 3, which is 1 by 3. Again the value of b is equals to f of 4. If we substitute the value of x, which is 4, 4 minus 1 upon 4 minus 3. 4 minus 1, which is 3, upon 4 minus 3, which is 1. We can write the value of f of b is also 3. So now by using the given function f of x is equals to x minus 1 upon x minus 3, we have to find f dash of x by differentiating with respect to x. So the derivative of f of x is f dash of x, and we take a derivative of x minus 1 upon x minus 3 by using the rules of u upon v. So we know that the u upon v is denominator into derivative of numerator minus numerator into derivative of denominator upon square of denominator. So x minus 3 as it is, derivative of x 1, and derivative of minus 1, which is 0, minus again x minus 1 as it is, derivative of x1 and the derivative of minus 3, which is 0, upon x minus 3 whole bracket square. So x minus 3 into 1, which is x minus 3, minus x minus minus plus 1 upon x minus 3 whole bracket square, plus x minus 1 x get cancelled. We can write f dash of x is equals to minus 3 plus 1, 2 upon x minus 3 bracket square. At x is equals to c, we can write f dash of c is equals to 2 upon c minus 3 bracket square. So the value of f dash of c, 2 upon c minus 3 bracket square, f of a 1 by 3, f of b 3. By using these both three values in equation 1 become f dash of c, left hand side, which is f dash of c, 2 upon c minus 3 bracket square is equals to f of b, which is 3, minus f of a, which is 1 by 3, upon b minus a, means 4 minus 0. If we take the cross product of these both terms, which is 3 into 3, 9 minus 1 upon 3. So we can write this 2 upon c minus 3 bracket square, minus 2 upon a value of f dash of c, which is minus 3 plus 1 minus 2. Here we can write minus 2 upon c minus 3 bracket square. If we take an equal denominator, 3 into 3 cross product 9 minus 1 upon 3 upon 4 minus 0, 4. We can write it 9 minus 1, which is 8 by 3 into 1 by 4. So 4 1, 8 2, we can write 2 by 3. C minus 3 bracket square is equals to 2 by 3. So if we take this 3, right side we can write 3 into c minus 3, or we can write c minus 3 is equals to under root of 2 by 3, taking square root both sides. So if we shift c minus 3 is equals to under root 2, so we can write taking square root both side, c minus 3 is equals to under root of 2 by 3. C, which is minus 3 become plus 3, it can write plus or minus under root of 2 by 3. So value of 2 plus or minus under root of 3 is greater than 0 and less than 4. Hence we can say that 3 plus or minus under root 2 by 3 plus or minus both value belongs to 0, 4. Hence we can say that LMVT is verified. Also we can solve these examples by using closed interval 4, 5. So by using 4, 5, you can solve this example for verified Lagrange's mean value theorem, which is homework for you.